So with these examples involving rocket cars, I'm trying to build an understanding of how you can take the concepts of rotational motion and apply them to more and more complicated systems and eventually kind of maybe more continuous, extended, rigid bodies that rotate. And one of the issues is how do you figure out like what the moment of inertia is? And so in the last example, we kind of did that. We had two equal rocket cars. That one I think was not quite totally aligned with the way it usually works when you look at the kinds of formulas that are available for moments of inertia. So this one is meant to be a little bit more of a bridge towards that. But again, we have two rocket cars that kind of symbolize just 2-point masses in a system. They're intended to be rigid here, right? So if we read this question, it says two rocket cars, each with a mass 1/2 m. Oh, that's also different. In the last example, I had each rocket car having mass m, but here I've made them 1/2 m. And the reason why is if I'm trying to get towards like maybe describing something like a spherical object with a uniform density, maybe it's rolling, maybe it's doing something. That's the kind of stuff we're trying to get to, right? You're not going to assign a mass m to every single molecule in that sphere, right? Mass m is going to be the total mass of that sphere. And so by analogy here, if the total mass of this system is m, then each rocket car must have a mass 1/2 m. So that's kind of the way I'm thinking about it. Similarly, the radial distance r, I could have done like r down here, right, for just the first rocket car, and then 2r. But instead I made r and 1/2 r. And the reason why is because when you look at the formulas that are available for moment of inertia, it is pretty conventional, with maybe some exceptions, but for many of them, the r that you plug into them is going to be, or going to correspond to the largest kind of radial distance of any part of that object. In that sense, like if it were the moment of inertia of a sphere, r is going to be the radius of the sphere, not the radius of like, half the sphere or something like that, right? Anyway, so it says here it's rigidly tethered though, because we want to imagine this is a model for a rigid body, right? While the outer rocket car, is applying a thrust force F. It says, what is the moment of inertia of the rigid two rocket car system and the resulting angular acceleration? So let me start with the moment of inertia part. And the concept is that we're going to sum over mass times radial distance squared for each of these. So if I start with that first rocket car, it has a mass equal to 1/2 m, right? And then it has a radial distance of 1/2 r. So I'm going to have to put that, I think, in a set of grouping symbols here, or a set of parentheses. Have the square kind of distribute over that. And let me see. I think that is going to be, correct me if I'm wrong. Oh, wait, this is a video. Nobody can correct me. Oh, well. Hopefully I'm not wrong. 1/8 mr squared, right? Oh, whoops. I'm supposed to... let me change the way I'm doing things a little bit here. We'll keep the tape rolling. That's what that's supposed to become, but I was supposed to add up both of them, not just state equals, because that we're really supposed to include all the objects in the system here. So that was a mistake on my part to just write equals there. So I'm just going to write that underneath. I've already started the second line, in other words, because I need to add mr squared for the second rocket car. And that one has a mass of 1/2 m again, but it is at the full radial distance r, so it's going to be 1/2 mr squared. So really that means we have 1/8 mr squared plus 1/2 mr squared. So now things are looking better, right? And I think 1/8 plus 1/2 is 5/8 mr squared. So that's my answer for moment of inertia. It also asks for angular acceleration, so that's where the Newton's second law for rotation comes in to help us, right? Because we do tau equals I alpha. This thrust, there's only one thrust force F. It is being applied at a radial distance from the center of rotation r. In other words, that's the moment arm at which it's being applied to. So torque tau is, oops, made a mark there, is equal to r times F. Quite simply, it's a right angle, so we don't need to worry about that sine theta. For I, we'll put in the 5/8 mr squared we just found. And then we put in the alpha, which we're trying to solve for. We can cancel off one of those r's. And it looks like if we cross multiply things. We're basically going to multiply both sides by 8/5 and divide by MR, excuse me. Alpha will then be equal to 8/5 F over MR. So those are the two. Let me maybe box my results here, right? This is what I'm shooting for when I check it with the slide. There it is. Hopefully those are expressions of the ones that come up now. Looks good.